200 coins. Some are heads and some are tails. But how many of each will there be? Is it likely that they're split half and half? Well, probably you'd say not. But what is the probability of an even split, 100 heads and 100 tails? Is it about a half, or nearer a tenth, or even a hundredth? In fact, you've seen that the probability of 100 heads and 100 tails is 200 choose 100 times 1 over 2 to the power 200. Now we can write the binomial coefficient in terms of factorials, but that still doesn't give us an idea of the numerical size. It's not easy to work out factorials of large numbers like 100 and 200, but there are many situations where we need to do so. David?
When I shuffle a pack of cards, what's the probability that I get them in numerical order within suits and the suits in a particular order? Well, there are 52 choices for the first card, 51 for the second, 50 for the third, and so on. 52 factorial different arrangements. So my probability is 1 over 52 factorial. And once again, we need to work out the factorial of a largish number, 52. You're already familiar with factorials of small integers. Factorial 3 is 6, factorial 4 is 24, factorial 5 is 120. But 9 factorial is about 1/3 of a million, and 10 factorial over 3 million. So how big are numbers like 52 factorial, 100 factorial, and 200 factorial? Well, n factorial grows very quickly as a function of n. For example, the number of seconds in a year is about only 11 factorial. The number of seconds from 0 AD until the end of 1990 is about 14 factorial. And the number of seconds since the Earth was formed, amazingly enough, is only about 19 factorial. Most pocket calculators are able to give you 52 factorial to 3 or 4 significant figures, but they just don't have enough memory to hold 200 factorial or even 100 factorial. However, in the 18th century, people were interested in analysing gambling problems like this one. And to help them, the mathematicians Stirling, de Moivre, and Euler found a practical way of estimating factorials. This estimate is called Stirling's formula. Now, its derivation involves integration. So let's begin by reviewing what we understand by integration. The integral is a mathematical way of describing the area between a curve and the x-axis over an interval. We begin by dividing the closed interval AB into a finite number of parts. This division is called a partition P of AB, and the length of the largest subinterval is called the mesh of P. First, we erect on each subinterval the smallest rectangle still enclosing the curve. We call the sum of the areas of these rectangles the upper Riemann sum for the function f with respect to the partition P, and we denote it by u of fp. Certainly, the area under the curve is less than u of fp. Similarly, we form the lower Riemann sum L of fp, the sum of the areas of the largest rectangles which will fit under the curve. And the lower sum L of fp is less than or equal to the upper sum u of fp. We can make the mesh smaller by choosing more points in the partition. The upper sum decreases and the lower sum increases. For this curve, it looks as if we could get upper and lower sums closer and closer to a common value by choosing smaller and smaller mesh sizes. That's what we mean by integrable. Now, upper sums are always greater than lower sums. So it follows that sup of LFP is less than or equal to inf of UFP. We call sup of L the lower integral of f over AB, and we call inf of u the upper integral of f over AB. Now, If f is a bounded function and ab a bounded interval, these upper and lower integrals must exist. In cases where they are equal, we say that f is integrable over ab. If f is integrable, then sup of L equals inf of u. So there must be partitions P for which the lower sum and upper sum are as close to each other as we please. That is, given any epsilon greater than 0, we can find a partition P such that u minus L is less than epsilon. We often use this criterion as a test for integrability.
Well, it is useful to have a relatively simple test for integrability, even if it doesn't tell us the value of the integral. With this test, we can, for example, show that every continuous function is integrable. But here's a function, and it's not continuous, but it is increasing from a to b. And the difference between the upper and the lower sums is the area of these small rectangles. Can we make this area as small as we wish? In other words, is this function integrable? Here's the graph of f with the upper and lower sum rectangles shown for some partition P. And here's a neat way for estimating their difference. We'll slide the first difference rectangle to the left, to the y-axis. Its bottom edge is at height f of a. Now we do the same thing for the next rectangle. Because f is increasing, it fits above the first one. And so on, for all the rectangles. They all fit inside a box of height f of b minus f of a, and of width the mesh of P. So the area is less than some multiple of the mesh of P. And by making the mesh of P smaller, we can make this area as small as we like. This means that the difference between the upper and the lower sums can be made as small as we like, less than epsilon, and this increasing function is integrable in spite of being discontinuous. Now this is an increasing function, but we could have done a very similar thing for a decreasing function. So what we have shown essentially is that any monotonic function is integrable. Now we're going to look at some particular monotonic functions. Because they are monotonic, we know that they're integrable, and we can use the fundamental theorem of calculus to find their integrals. We're going to use those integrals and a particular partition to obtain some results about series.
Here's the first graph, y equals 1 over x squared. And using the fundamental theorem of calculus, we can work out the area from x equals 1 to n. It's equal to the integral of 1 over x squared from 1 to n, and that's 1 minus 1 over n. Now we use partitions to get the integral. So let's look at a particular partition of the interval from 1 to n, the one where the partition points are the integers. Here's the area in which we are interested, with the interval divided into subintervals of length 1. Now let's look at the lower sum for this partition. All the rectangles have width 1. And because this function is decreasing, the height of the first rectangle is the value of the function at 2. That's 1 over 2 squared. So the area of the first rectangle is also 1 over 2 squared. Similarly, the second rectangle has area 1 over 3 squared, and so on, up to 1 over n squared. So the lower sum for this partition is sigma 1 over k squared from k equals 2 to n. And that's less than the area under the curve, 1 minus 1 over n. If we add on the first term of this series, a square of side 1, we get sigma 1 over k squared from 1 to n. And this is less than or equal to 2 minus 1 over n. So the partial sums of the series sigma 1 over k squared are all less than 2. And it follows that since the partial sums form an increasing sequence, bounded above by 2, the infinite series sigma 1 over k squared must converge. So, knowing that the function 1 over x squared is integrable, allows us to say something about the series sigma 1 over k squared. We're able to confirm that it is convergent. Well, can we do a similar sort of thing for the harmonic series sigma 1 over k? Let's look at the graph y equals 1 over x. Here it is. This too is monotonic, so it's integrable. And this area between x equals 1 and n is equal to the integral of 1 over x from 1 to n. And that's log n. Again, let's take the integer points as the partition points in the interval. Let's start as before by looking at the lower sum for this partition. Because the rectangles have width 1, the lower sum is a half plus a third and so on up to 1 over n. So sigma 1 over k from 2 to n is less than log n. Again, adding in 1 for the first term of the series, sigma 1 over k from 1 to n is less than 1 plus log n. But the trouble here seems to be that we've shown that the partial sums are less than something. Because we know that the harmonic series is divergent, it would be more useful to have a lower bound for sigma 1 over k. So let's try upper sums instead. If we move all the rectangles to the right, we have essentially an upper sum for the area under y equals 1 over x from 1 to n. Sigma 1 over k from 1 to n minus 1 is greater than log n. The sum runs from 1 to n minus 1 now because the nth rectangle isn't inside the interval 1 to n. But if we include it on both sides, we get that sigma 1 over k from 1 to n is greater than log n plus 1 over n. Now the right-hand side tends to infinity, which shows that the harmonic series must be divergent. Now we've just seen that we could associate the terms of infinite series sigma 1 over k squared and sigma 1 over k with values of functions 1 over x squared and 1 over x, and use the integrability of these functions to deduce convergence or divergence of the corresponding series. In fact, what we were really doing was using the so-called integral test. This says that if we have a function f, which is decreasing and tends to 0, then the series sigma fn converges if the integral of f from 1 to n is bounded, and the series sigma fn diverges if the integral of f from 1 to n is unbounded. And then, what's more, the nth partial sum of the series is about the same as the integral from 1 to n for large n. So you see that by associating the terms of an infinite series with values of a function and using the integers as partition points, we can deduce convergence or divergence of the corresponding series.
That's a useful result, but how is it going to help us with working out 200 factorial, or n factorial for large n? Well, n factorial is a rather nasty product, and one way we simplify products is to take logs. What does that give us? Well, log n factorial is log of 1 times 2 times 3, and so on up to n. That's the same as log of 1 plus log of 2, and so on up to log n. And we can write that as sigma log k from 1 to n. Obviously, the series sigma log k is divergent because its terms are non-null. But it does have something to do with this graph. The terms of the series sigma log k are the values of this function at integer points. Also, this function is monotonic. It's increasing this time, so it is integrable. The integral of log x is x log x minus x. So this area is n log n minus n minus 1. Taking a partition at integer points and looking at the lower sum, the areas of these rectangles are 0, which is log 1, log 2, log 3, and so on, up to log of n minus 1. So the lower estimate is sigma log k from 1 to n minus 1, which is log of n minus 1 factorial. Similarly, looking at the upper sum, the areas of the rectangles are log 2, log 3, and so on up to log n. So, since log of 1 is equal to 0, the upper estimate is sigma log k from 1 to n, or log of n factorial. So it seems that we might get an estimate for log of n factorial from all of this. Unfortunately, it turns out that this is not good enough for practical purposes. Neither the upper nor the lower sum is close enough to the area. We have to get a better estimate for the area, and we could do this by averaging these two. This corresponds to approximating the area by trapezia. Now this area is half of log n minus 1 factorial plus log n factorial. But unfortunately, this still is not a good enough approximation for our purposes. The area underneath the log curve is made up of the trapezia and these little slivers. Actually, what we need is to estimate the area of these slivers. Here's the area again, approximated by trapezia. What we want is to estimate the total area of the little slivers like this one. We'll call the total area of the slivers from 1 to n Cn. So Cn is the area under the curve minus the area of the trapezia. The integral is n log n minus n plus 1. And the term on the right can be simplified. Log of n minus 1 factorial plus log n is log of n factorial. So, adding and subtracting log n, the right-hand term becomes log of n factorial minus a half log n, giving us this for Cn. Now, Cn is an increasing sequence, and it turns out, fortunately, that it is bounded, and so it tends to a limit. Now, why is Cn bounded? Here's the picture for n is equal to 4. C4 is the area of these 4 slivers. The 4th sliver lies below this dotted line, which is the line bounding the 3rd sliver. If we slide the 4th sliver down, it fits in below the 3rd one. Both of these now lie below the line bounding the 2nd sliver. We can slide the pair down to lie below it. Finally, all 3 can be slid down below the 1st. They have a common vertex, but they don't overlap. And they all fit inside this rectangle. Because the curve is the log curve, the rectangle height is log 2, and its width is 1. So its area is log 2. And it doesn't matter how many slivers we have, each extra one fits below the previous ones. So Cn, the area of n slivers, is an increasing sequence bounded above by log 2. So, what is the limit of the sequence Cn?
Well, here's the expression for Cn. So let's try to simplify it by making each of the terms log of something. Then I can combine them all as a single log. So this first term is log of n to the n. This is log of e to the n minus 1. This term's all right as it is. This last term is log of n to the half. So I can combine them all to get log of n to the n divided by e to the n minus 1 divided by factorial n times n to the half. So if I exponentiate Cn, I get this ratio. And because this expression Cn tends to a limit, so does its exponential. So this ratio, let's call it An, tends to some number, I'll call it L. Now, I already know the limit of something involving factorial n. it's Wallace's formula. The ratio of factorial n squared over factorial 2n suggests that I should work out the ratio of an squared over a2n. Now, with a bit of arithmetic, here's what I get. An squared over 2n equals this expression, and so this. So now let's take the limit of both sides. The left-hand side tends to L squared over L, and that's just L. On the right, Wallace's formula tells me that this first bit tends to 1 over root pi. So I get E over root 2 pi for L. So this ratio also tends to E over root 2 pi. Now for large n, this ratio and E over root 2 pi are more or less equal. So I can think of this limit as being a sort of approximation. And if I then rearrange the terms here, I get that factorial n is more or less the same as root 2 pi n times n over e to the n. And this approximation to factorial n is called Stirling's formula. And the larger the value of n, the better the approximation. Stirling's formula gives factorial 5 as 118, an error of just under 2%. But for 100 factorial, the error is only about 1/12%. And I can now use Stirling's formula to estimate the probability of a pack of cards being dealt in a specified order. Remember, that probability was 152 factorial. If I put 52 in place of n in Stirling's formula, I get that factorial 52 is about root 2 pi times 52 over e to the power 52. And that's about 10 to the power 68. So the probability of getting the cards in order is pretty small. And Stirling's formula should help too with Ian's coin problem.
Remember, the probability we want is this. So I need to find 100 factorial and 200 factorial. Putting n is equal to 100 in Stirling's formula gives me this. And when n is 200, I get this. So 100 factorial all squared is this. Now I need to put these expressions into the probability, which you remember is this, 200 factorial over 100 factorial all squared multiplied by 1 over 2 to the power 200. This is what I get, and as you can see, there's quite a lot of cancelling I can do here, and I'm left with this fairly simple expression, 1 over 10 root pi, roughly 1 in 18. So the probability of equal numbers of heads and tails in 200 coins is about 1 in 18. And that's quite a bit bigger than I had expected. Are you getting anywhere? Did you know there was a German lunatic called Leuben who was convinced that if he shuffled cards for long enough like that, he'd find them in a particular order? He shuffled cards 10 hours a day, finally succeeding after about 20 years, something over 4 million shuffles.
Well, when the probability of getting it right is about 1/10 to the power 68, I guess he was pretty lucky to get it right after only 4 million goes.
You think he knew Stirling's formula?